All right, guys, in this video lesson, we're going to take a look at doing Lewis structures, but instead of just doing your basic parameters, we're going to take a look at it through the idea of some exceptions that we have to this, okay? So in the world of chemistry, we always have our rules and our policies that we have to follow, and then we always have exceptions, okay? So there are four things that we're going to take a look at today in terms of those exceptions. We have dealing with hydrogen and 2 electrons, phosphorus and sulfur expanding, boron reducing, and then what happens if we have an odd number of electrons on a compound, okay? So let's tackle hydrogen first. Now, hydrogen is stable if it only has 2 electrons on that, okay? And if we take a look at why that would be, well, first of all, if we take a look at hydrogen in terms of its electron configuration, hydrogen is a 1s1, okay? Which means it's only in the first energy level and there's only 1 electron available for that. So hydrogen, when it bonds, only starts with 1 electron. Now, being that it's in the first energy level and it wants to be like the noble gas helium, remember helium only has 2 electrons on it, okay? So in that first energy level, because we have no p-shaped orbitals, we have no d-shaped orbitals, we only have the s orbital, 2 is actually our magic number, not 8, okay? So hydrogen, when it forms a bond with anything else, even with itself, take a look at that, is going to share just one of its electrons and form 1 bond. So as a result, hydrogen will always form a single bond, and it will always be on the outside of any molecule that it forms, okay? Those are some nice always that we can use for hydrogen, okay? So looking at our example down here, being methane, when hydrogen forms inside this, the carbon and hydrogen are going to form single bond, single bond, single bond, single bond. Now this is just an example to that exception, for our exceptions. There are other things for hydrogen that do this. But for hydrogen, what's nice is every time you write hydrogen, it will always be on the outside. You will always use a single bond. Okay, it'll never be double bonded, it'll never be triple bonded, there'll never be unshared pairs of electrons on it. It's always the same, okay? But you just need to accept the fact that it's not going to be 8, it's going to be 2 for hydrogen. Now, moving on to the next one, phosphorus and sulfur, if we take a look at their electron configurations, phosphorus, if we go to its noble gas configuration, is neon essentially, and then it is a 3s2 3p3, okay? Which means it has, 2 valence electrons in the s and 3 more here. So phosphorus has a total of 1, 2, 3, 4, 5 valence electrons around it. Now I'm drawing it this way on purpose. Normally we would say phosphorus, you'd pair 1 up and then it'd have 3 in the quadrants, okay? But phosphorus can expand its octet. So I kind of do it this way to show you that there's actually 1, 2, 3, 4, 5 potential places that it can share its 5 valence electrons. Now, it can do that because once we get to the third energy level, we have the S-shaped orbitals, we have the P-shaped orbitals, and the D-shaped orbitals available. Now, the D is normally empty when it comes to that third energy level, right? It exists, it can be used, but it's empty for phosphorus and sulfur. So what phosphorus does, it uses that 1s, it uses all 3 p's, and it uses one of those d orbitals to create 5 bonding regions that are the hybrid. Normally, we do an octet where we use the 1s and the 3 p's to get 4 bonding regions. So phosphorus just adds that d in to give us a 5th one, okay? As a result, if we go back to our screen now, we see things like phosphorus pentachloride exists, where phosphorus actually forms 1, 2, 3, 4, 5 bonds with it, with the chlorines around it, okay? This gives phosphorus a lot more flexibility because if needed, it can actually go to 5 bonds, okay? It doesn't always do it, but only if it needs to. Sulfur is the same way. The only difference is with sulfur, because sulfur starts off with 6 unshared pairs, 6 valence electrons, it actually has 1, 2, 3, 4, 5, 6 different potential sharing that goes on. So it's using its s orbital, it's using all 3 p orbitals, and it's actually using 2 of the available 5 d orbitals for a total of 6 to share instead, okay? Same reason, just because sulfur starts with 6, it then can use more of that d orbital to make that happen, okay? Now, there are other elements on the periodic table that also expand their octets. Okay? For our purposes, we're only going to ask you to remember phosphorus and sulfur, because they're the ones who most commonly do that, and they're the ones that we're going to see examples of that in the chemistry that we do this year. Okay? Now, boron, our next kind of deal, is the exact opposite of phosphorus and sulfur. It's more like hydrogen, where boron can actually reduce its octet. Okay? Now, boron starts, if we take a look at that, boron only has 1, 2, 3 valence electrons around it. So if it shares, let's say with hydrogen as an example, 3 different times, it uses up all the electrons it has available in terms of its sharing. Okay? Now, not ideal for boron, but it does do this where it will form molecules that only have 3 shared places with it for a total of 6 valence electrons. Okay? Does this make boron less stable? Absolutely. Okay? But because boron is not very electronegative, because boron doesn't do a good job of gaining electrons, typically what happens is things like fluorine will create these bonds but not give up these extra electrons to let boron have 8. They won't put a double bond in here. They'll keep them. So boron just gets reduced down and say, well, you only get 6. And boron has kind of to live with it. Okay? So it does happen for boron. So that's one of our exceptions we're going to see also. Now the last one is there are compounds that exist. They're not as stable as other compounds, but there are compounds that exist that have an odd number of electrons. Okay? So one very common example is nitrogen dioxide that we see here. So if we count up our total available electrons here, nitrogen has 5, and the oxygen each has 6. So we have 12 here plus the 5. We have 17 electrons. Okay? So what do we do when we have an odd number of electrons? Okay? Well, somebody on that group has to have less than 8. That's the only possibility. Okay? Because if everything had 8, that'd be an even number of electrons. So somebody here has to take the odd number of electrons. Now, there is a mathematical way to figure out who is supposed to get this. It goes through a process called formal charges. If you're interested in that, you can look up formal charges and how formal charges work. It's actually a way to determine of the 3, elements here, this oxygen, this nitrogen, or this oxygen, which one gets the single. For our purposes here, I just want you to acknowledge that this can happen. And I want you to be able to build a Lewis structure that potentially could be correct with that odd number in it. So I'm not going to grade you on, does it belong here, or should the nitrogen have the odd number, or should oxygen have the odd number? I don't care which one you give the odd one to. If you go to AP chemistry or college chemistry, they'll give you that formal charges to be able to solve that exactly. But for us, just recognizing that, yes, it's possible. If we do get an odd number, something in here is going to end up only having 7, and that's okay. Okay? Everything else should have 8, but one of them is going to end up with 7, making a less stable molecule. All right? So those are 4 different kind of exceptions to our octet that we need to deal with. When we're working through practicing this and kind of becoming confident with our Lewis structures, here are 4 examples, 4 more, and 4 more that we want to work our way through. These practice examples are exactly the same as worksheet number 1 in your student files. Okay, so remember, your student files can be accessed either through Google Drive. That's a folder I shared with you at the beginning of the year, or you can actually go in through Schoology and find your student files in your modules. Okay, so these I would highly recommend you practicing for additional practice. A couple of things to make a note of that you might see on here going, what should I do with that? The first is sulfate, SO4 -2, and maybe carbonate over here, CO3 -2. Okay? If you have ions like we see here that you're working with, the trick to ions, if it's a -2 charge, well, remember our first rule for building our Lewis structures is count up your total electrons. Okay? Well, sulfur has 6. Each oxygen has 6 also. So we actually have, 4 times 6 is 24 plus 6 more is 30. So we have 30 available electrons for SO4, but it's a -2 charge. So you just put 2 more on, okay? So this has its 6, the 24, and 2 more. So there's a total of 32 electrons you can work with here. Same thing over here. Carbon has 4. Each oxygen has 6, so there's 18 plus 4. So that gives you 22 electrons. The -2 gives you 2 more, so now you have 24 electrons to work with here, okay? So you're going to see that when you have these extra electrons, to use, it actually makes the Lewis structures come out more normal or more simplified, okay? So that's really easy to do. If you have negative charges, you just add more electrons in. If you get one, there's no example here, but if you get one that's a positive charge, you just take an electron away, okay? And again, remember, we don't want to have individual atoms owning electrons. So you're not putting 2 on the oxygen, you're not putting 2 on the sulfur. You just get 2 extra electrons to put wherever you want when you're doing your Lewis structures, okay? The other things you might start to notice is some of these more advanced ones get to be longer and bigger, okay? When you start to see that, especially when you have carbons and hydrogens in organic molecules, or these are called hydrocarbons, you want to draw them the way that you see them written, okay? And remembering that hydrogen is always on the outside, okay? So for example, CH2O, what we want to do is say, okay, carbon is written first, so that's going to be in our middle. There's 2 hydrogens coming off of that, so you're going to have 2 hydrogens coming off of it. And then you're going to have an oxygen. Now, oxygen can't attach to hydrogen because it only can have 1 bond. So the only other place it can be is attaching to the carbon, okay? Same thing down here with our C2H5OH, okay? We see carbon in the middle, but there's 2 of them. So I would start by putting 2 carbons in the middle. You have 5 hydrogens coming off of those. So you have 1, 2, 3, 4, 5 hydrogens coming off of that. And then you have another oxygen. So that oxygen comes off of a carbon and then another hydrogen outside of that, okay? So you start to see that we can start to build these structures with kind of how you read them. So we see C2 is our middle, put 5 hydrogens off of that, attach an oxygen, and put a hydrogen outside of that, okay? That's useful because if we had C2H6 here, we would never know that this 1 hydrogen actually comes off the oxygen, okay? And again, it takes a little bit of practice to figure these out, but that's kind of helpful for that. You may notice over here we have HCN. Well, the H is written first to tell you that the hydrogen attaches to the carbon, not the nitrogen, okay? So carbon will still be your center because hydrogen can never be in the center. Kind of help you with that one. Up here with N2O4, again, put the 2 nitrogens in the center and then put 4 oxygens around those 2 nitrogens. When in doubt, make it as symmetrical looking as you possibly can because in nature, symmetry wins out, okay? So if you're not sure how to do something, try to make it symmetrical. That tends to give you the better result when building your Lewis structures. All right, guys, that is everything for this. It is the expectation that you're going to be able to draw these. There is lots of extra practice. There's actually 2 additional worksheets besides this one for more practice for you. So take the time in and practice them. Check out the answer keys. And as always, ask me questions if you need them. Thank you.